Okay, now we're going to move on and start taking a look at different kinds of force applications. So we're pretty much done with normal force right now. So now what I'm going to start looking at is stresses in shafts. Now, as we look at shafts, we're applying force in a slightly different manner because now we are twisting things. Torque is a moment that tends to twist a member about its longitudinal axis. And as you probably remember from your physics class and more recently your mechanics and statics classes, that a moment is going to be a force applied at a distance. But once again, that doesn't matter for strength of materials because I do not care about external torques. I care about internal torques. And just the same way that we can take a bar that has multiple forces applied to it, we can do the same thing with torques because all that stuff's additive, and we make our cuts at some place and we go, okay, I need to make sure that everything's in static equilibrium, so I'm going to calculate out what the internal torque is to make sure that there's no motion. So we have the same thing going on. So let's take a look inside our bar. So I'm going to cut that in there. And so now if I look at the bar, I've made a cut in the middle of my bar here. So I'm looking at that T posit, that T prime is that external force. And so what I'm looking at is I'm trying to calculate out what's the internal torque in this spot. This one's easy because my T prime has to be opposed by torque, which is going to be the exact same. So let's look at this in general. So in general, if I look, I can find a little differential element like I've shown here, and it'll give me a differential element of force. And so what I'm going to say is, okay, well, the torque is going to be, I'm going to look at that differential element, so dF. And so what is torque? Torque is going to be the amount of force times the lever arm. So dF, we're going to be integrating all those together. And so we represent the radius here by lowercase rho. And I'm sure that you're familiar with that. So we're just reminding you that that's rho. So torque is going to be that force times that distance to get there. And the thing is we know what kind of stresses that we're going to be dealing with here because we are twisting, we are sliding, we are not applying a normal force, but we're applying a shear force. So, since it's force over area, I can go, well, that force is going to be my shear stress times whatever little bit of area that I'm looking at. Therefore, I can take this and plug this back into my equation here. And so instead of using differential of force, we can go about using the differential of area. And then we can say that our torque is going to be equal to the integration of all of those radii times the stress dA. And so we'll be coming back and using this equation to put some things up a little bit later. So we know that our internal stresses will have to be shear stresses because I am twisting things. I'm sliding. So not a normal force. That's an important thing to remember. So let's look a little bit at twisting. And so what this picture here is using is we have kind of a barrel with slats on it. And so as we twist the thing, you'll notice the slats all are now at an angle. They're no longer straight, but they're all the same distance. So the length has remained unchanged. They're all still flat. All that's changed is the angle. And they're all still, all these little lines are still parallel to each other. Now that's an important distinction because as we look at it, here's another picture. So I have my shaft here before deformation. You can see I've got this perfect little grid work on it. Everything's 90 degrees and all that. I apply a torque to it and start to twist it. The circles here all remain circles. They just kind of turn in place. Nothing happens. So this circular cross-section here is the exact same as that circular cross-section there because all I've done is spun into place. The only change that I have as I make that twist is with these lines, because these lines are no longer straight. No, excuse me, the lines are straight, but they're no longer kind of parallel there. As you'll notice, they start to twist, and they're going to start to roll off. And in fact, when you do this one in the lab, there's an experiment where you'll chuck up a piece of material, and you'll just keep spinning it, and keep spinning it, and 10, 15 rotations, and you're going to see these lines are going to start to candy cane. They're going to like stripe along the thing. And so it's a really neat little effect. But so what's going on is that's our geometric change that we have associated with twisting, is we're going to have this angle change. So now as we look at this and we start following this line down the shaft, we can see that it's starting to twist. So the angle changes as we move along. If we say this is the x direction, there's a function of the angle as we move along x. So let's take a look at some of the geometry that's going on here. And we're going to start defining a couple of important aspects as we go along. So we're going to bust out a little bit of geometry here. Let me see if I've got a, oh, I thought I had a zoomed up picture of that, but I guess not. So what I want to look at is, I want to look at two different things. First of all, I want you to take a look at the side profile right here. And so what we're looking at is we've got this little angle of the new line as opposed to the original line. And we're familiar with this angle because this is gamma. So remember, gamma is what we call a shear angle. And so that is what's going along the side. So we calculate it just like normal. But what I want to look at is, I want to look at what's going on here at the end. So we're going to use a little bit of geometry to calculate that. So if we move over to here to this figure that's labeled 0503, so as we start to spin the axis, now this line in the center forms a plane. And then this line with the center line forms another plane. So what we're looking at now is we're looking at how those two are changing, which is what we can see if we look over in this other picture here and I look at this element and I look up. Here's my original plane, so that would be this line BC, or excuse me, BA. And then we have this plane, oops, sorry about that, go away. We have this plane here, which represents that BA prime. And so we're gonna focus on some geometry, what's going on right here. And so what I want to look at is I want to take a look at the arc length. And where did B go? So specifically, notice this little region here that's a little bit different shaded. So that is the change between the two planes. In fact, you can see there's my shear angle that's in there. So D to B. So I want to look at that arc length. I'm going to bust out some old geometry. So the arc length between D to B is going to be, well, rho. Because once again, this is our radius to get to the out. But we need to define something else now, because there is going to be an angle on that flat face. So if I look down here and look at the end of my shaft, you'll notice that between those two planes, we've got a little triangle that's formed. We have an angle between the two of them. So what we're going to do is we're going to define that angle, and we're going to call that, as we continue our classical Greek education, what is this? Well, this is uppercase phi. And so uppercase phi is we're going to define that as what we're going to call the angle of twist. And so the angle of twist is the angular dimension at the end of our shaft. Now we can do this at any cross section in there, because once again, as we've talked about before, this is going to change as a function of x. So the shorter you are, the smaller angle of twist that you've got, and the longer you go along the shaft, you're going to get more and more angle of twist. So let's go back to our arc length dB. How do we calculate that? Well, that would be the radius times the angle that it swept through. So the change in the angle of twist. And as we also look at that, we can say that that's going to be the change in the x dimension, which would be the dimension along here. So the length of the x dimension times gamma. So just some straight out geometry from back. I don't know when you guys take geometry. I think I did this in like 9th grade. So I know we're trying to pull some knowledge from probably high school, but that's okay. We're just going to set some stuff up and then deal with it. But the important thing is what we're looking at here is d phi and dx are basically differentials. So if I ignore now, I don't need that because I've equated the other two, and I can sit here and go, oh, those are differentials. I can separate out the variables and rearrange this, and I can get to, okay, well, my shear angle is going to be equal to my radius times how my angle of twist changes with x. So at this point, this video is getting a little bit long. What we're going to do is in the next video, we're going to pick up right here and see how we can put this together.